Let's jump right in. So systems such as operating systems, cloud infrastructure, and networking have historically been written in languages like C or C++, and have thus been rife with memory safety vulnerabilities. I'm just showing some examples here. And for instance, to underscore this point, in the Chromium projects, it was found that 70% of the security critical bugs have been found to be memory safety issues. And in the past few years, we've seen a shift where we are now seeing safe systems programming languages, chief among them Rust, that are being used in these fields in order to mitigate these issues. For example, Microsoft has been rewriting core parts of Windows in Rust. Linux now allows writing drivers in Rust. And Google is adopting Rust for core parts of their Android operating system. And in fact, this is not just hype. This seems to be having a real positive impact on the safety of these systems in practice. So for instance, with this last move, Google has observed a significant drop in the number and the severity of memory safety vulnerabilities in Android. All right, so let's rewrite everything in Rust then, right? Not so quick. All of the systems that I've shown were carefully built by scores of engineers over decades. So rewriting this code is not going to happen overnight, if ever. In addition to that, even when we're writing new software, developers are often interacting with libraries such as cryptography libraries, data stores, compression libraries, or image and video encoders, most of which are probably going to be written in C. So in summary, rewriting everything is impractical. Even if we look past the prohibitive cost and time required, companies might be lacking domain expertise, so never roll your own crypto, or they might be forced to use certain libraries that have undergone certification as part of industrial certification requirements. So today, I'm going to tell you about our approach and framework, Omniglot. Omniglot allows developers to build systems in Rust that safely interact with foreign code with minimal overheads. Before I talk about how Omniglot achieves this, let's first look at the problems that arise when Rust interacts with C today. When integrating a foreign library into a Rust application, it runs in the same address space with the same privileges as Rust. And while this means that calling into the library is efficient, it's a mere function call and the ability to share memory, it also means that any bug of the foreign library endangers the safety of the Rust application, for instance, by overwriting any of its private objects. Prior approaches have recognized this issue, and they propose to use memory isolation to restrict the portion of the address space that's available for foreign libraries. And while this is effective for a large number of bugs that directly violate the memory safety of the library, as we'll see throughout this talk, this alone is insufficient. And that is because for a foreign function interface to be useful, the host program needs to be able to communicate with that library, such as through function calls, arguments, return values, and most efficiently, shared memory. And it is this exact communication that opens up a number of additional ways in which incorrect foreign code or bindings can endanger Rust's safety. Omniglot solves these issues by interposing on Rust's foreign function interface. It integrates with existing memory isolation primitive, and then additionally and crucially, it mediates all interactions with foreign code to ensure that even untrusted foreign libraries can't endanger Rust's soundness. In this talk, I want to focus on two of Omniglot's key mechanisms, how it validates values and how it reasons about interactions with foreign memory. We start by illustrating how violating Rust's invariants concerning valid values can introduce misbehavior. So on this slide here, I'm showing a simple foreign function binding for a function called AES encrypt. This function promises to encrypt the buffer that we provide as an argument, and it returns a bool to indicate whether this operation was successful. And let's just assume that the AES encrypt function that's, for instance, written in C is actually memory safe, meaning that the only memory that it touches is the memory that Rust expects it to touch, such as the buffer, the length, and the return value. Additionally, we define a Rust enum called message with two variants, encrypted and unencrypted, and associated data. This data structure is similar to a tagged union in C, if you're familiar with that. The program now calls the AES encrypt function, which takes the return boolean, the program then takes the returned boolean and uses it to construct a new message encrypted instance. Unfortunately, even such a simple and commonplace operation can be risky in the presence of foreign code. And this is because of a clever optimization that Rust is able to perform called niche filling. When we look at the memory layout of the outer enum here, the message enum, we expect it to have the following fields: a discriminant, that indicates which variant is currently active, and then depending on that discriminant, for the encrypted case, either a Boolean and a vector, or for the unencrypted case, a C string pointer. However, Rust is able to recognize that the Boolean can only contain values in 0 or 1. At the same time, it knows that the discriminant used to be able to distinguish between those two variants contains a mere 1 bit of information. Thus, Rust is able to merge those two fields into one. So in this new field, if it contains a proper Boolean, that indicates that the encrypted variant is active, and then it uses another uninhabited value of that type to represent that the unencrypted variant is active. This optimization is nice. It saves a word of memory and is just one example of the many optimization that Rust performs as part of its zero-cost abstractions. But it is tricky in the presence of foreign code, and that is because we have very few guarantees that the value that C returns when we call this function actually adheres to what Rust thinks a Boolean should look like. If C, for instance, returns as a 2, which it could do, then Rust will simply store that value in this field, but then upon reading that type back, it is going to assume that the unencrypted variant is active instead, and is going to misinterpret a type of vector as C-string, read past the end of this non-null terminated buffer, and result in an out-of-bounds access. If we look at the Rust reference, we see that the Boolean invariant is just one example of the many invariants that Rust places on its types. And for each such type, it might be that a foreign language does not have a corresponding type, that its corresponding type has slightly different semantics from Rust type, or that a foreign library is simply buggy and does not adhere to even its own language's requirements. Whatever the cause of the type mismatch in the previous example, it demonstrates that using Rust's native unsafe foreign function interface with incorrect foreign libraries or bindings exposes programs to risks, even if those libraries that it interacts with are themselves memory safe. Omniglot interposes on this interface to catch and prevent such issues before they can manifest in undefined behavior. And for the example of valid values in particular, it uses a trick. Instead of invoking foreign code with its proclaim type signature, Omniglot defines another function binding with a set of weaker assumptions. So for instance, in this example, this could mean instead of returning a Boolean, it could return a type cchar that has identical size and alignment to the C Boolean type, but crucially, does not have the same restriction on the valid set of values. However, this type is also less useful. The developer expected to be returned a Boolean, and now they have to deal with an integer, so what's all that about? To solve this, we generate runtime wrappers that then call these weaker functions internally and perform a set of runtime checks to recover the original type or form a type validation error. In this case, for the Boolean example, it's as simple as checking that this value is not larger than 1. Then developers can use this safe wrapper, which apart from forcing them to handle the possible type validation error, has an identical signature to the original function binding. Okay, so the previous approach shows how we can deal with values that are provided by foreign code but are stored in Rust's own memory. However, next to these own values, Rust might need to access values that are located in the foreign library's memory directly through references. And that, in turn, exposes us to another issue, namely that of upholding Rust's invariant of aliasing XOR mutability. In essence, this rule states that there can never be two Rust references pointing to overlapping memory if at least one of them is a mutable Rust reference. This invariant is crucial to uphold because Rust bases many compiler optimizations on it, and violations of it have resulted in real-world security issues in practice. At the same time, it's difficult because in many cases, developers can't reason about the provenance of pointers as they're flowing through a foreign library. Let's illustrate this through a simple example. Here I'm showing a library that implements a stack data structure with 3 common methods, push, peek, and pop. And let's just say that our Rust program first wants to inspect the stack's topmost element. So it calls peek. Peek returns a pointer, and Rust does not directly allow reading from or writing to raw pointers. Instead, a developer has to use unsafe to convert this to a Rust reference, which they can then use to inspect the value. Now the Rust program wants to change this value, so we call peek again, getting the same pointer back, and this time upgrading it into a mutable Rust reference using the unsafe keyword here. Then we can write to that value. Unfortunately, this is already sufficient to break the invariant, because when we now inspect the contents of that first reference, we see that the previous write operation has modified its contents as well. They're pointed to the same element after all, despite this being an immutable reference. And while this was predictable in the simple example, it's much harder to reason about in the general case. For example, a library might return a pointer to an object, and then another pointer to a field within that object, also producing aliasing. In the worst case, we have to assume that given an untrusted foreign library, all pointers could potentially be aliasing each other. Therefore, Omniglot must mechanically prevent developers from introducing any such unsound mutable aliasing. To solve this, we design a type infrastructure to model all interactions with foreign memory that is able to statically reject any possible unsound mutable aliasing. This type infrastructure works by progressively gaining invariance over foreign memory through type-state transitions. And these type-state transitions start from a raw pointer into foreign memory, as we've seen on the previous slide, which was used to be, or can be safely exchanged between Rust and foreign code. And because it is neither readable nor writable, it can be misaligned, dangling, or point to an invalid value. To obtain a more useful type, developers can use an upgrade operation on this pointer by validating that it is well-aligned and entirely contained within memory belonging to the foreign library to be able to gain a safe write operation on that type. Finally, if they want to read the value that is contained behind that reference, they can validate it, which ensures that the reference's point t is a valid value using the exact mechanism that we've shown before. Right. And then we can also show these operations on a timeline, where we first upgrade a raw pointer to a mutable reference and then go from that to a readable reference. While each of these operations that I've just shown is safe in isolation, when we combine them with some other operations that Omniglot exposes, we can unfortunately again produce unsoundness. For example, when we call into a foreign library, it has access to all of its memory. So it could write potentially invalid values to memory that is currently backing a valid reference or validated reference, thus endangering its invariance beyond that type and making it dangerous to be retained beyond that point. A similar issue exists when we revoke memory of the foreign library by freeing it, if we have an active reference to that memory still, such as a mutable reference. To solve both these issues, we must temporally constrain the time that Omniglot's references are valid for. And we do so by introducing two marker types, an allocation scope represented as an orange square and access scope on the slide represented as a blue triangle. These are singleton types, meaning that we can only have one instance of these types per foreign library. And we use these types to bind Omniglot's references to the lifetimes, the Rust lifetimes of these scopes. For instance, the validate operation now takes a shared reference to the access scope marker, which ensures that it cannot outlive the point at which a unique reference of the same marker is going to be used. Then, we extend all operations that could endanger the validated type's invariance, namely that its point t is a valid value, to take such a unique reference. This is sufficient to let the Rust borrow checker ensure that no validated reference can live past the point of this dangerous operation, which we also illustrate on the timeline here. We use a quite similar approach for the issue around revoking allocations by binding mutable references to the lifetimes of an allocation scope marker, and then requiring all operations that could potentially free memory to take a unique reference to that marker. Then, no reference can outlive its underlying allocation. OK, so that was a lot. So let's revisit the stack example from before and see how these types change it. We can still inspect the stack's topmost element by calling peep, this time calling a safe upgrade method that binds it to an allocation scope and returns a reference that is bound to that scope, and then validating it against an access scope in a similar way. This allows us to inspect its current element. We can also still write the memory in quite a similar way by, again, upgrading another pointer to a reference, and then using a write operation, which now crucially takes a unique or mutable reference to an access scope. This closes the access scope that was open up until this point. And then, if we want to print the previous reference's value, we get a compiler error, which is because that reference was bound to the previous access scope, which automatically became inaccessible after issuing the write, thus eliminating any unsound mutable aliasing. All right, this concludes our exploration of two of Omniglot's core mechanisms, and we invite you to read the paper for more details. Now I want to briefly pop up a bit and talk about what all of this is useful for. We implement Omniglot prototypes for two types of systems: Linux user space using x86 memory protection keys as a memory isolation mechanism, which allows developers to use common, established, and optimized libraries safely. We evaluate Omniglot on 3 of those shown on the slide. And also we implement Omniglot for the TOC kernel, a security-focused operating system that is often used in embedded systems and hardware root of trust devices with the kernel built in Rust. And because these often need to use existing certified libraries, we also evaluate one such example, namely the OpenTitan cryptolib. As Omniglot does add safety guarantees, it does introduce overheads as well. And we quantify these overheads by evaluating against existing work. And here we can see the performance of an image decompression routine as a function of the image size in libpng, using both Rust's native foreign function interface and using Sandcrust, which is an alternative approach, which delivers an equivalent set of guarantees that Omniglot provides, but uses inter-process communication and serialization and copying instead. We can see that Omniglot significantly outperforms this work due to its ability to directly interact with foreign memory without copying. If we look at a more detailed breakdown of our overheads, we can see that most of the overheads come from memory isolation alone in these two columns. And in addition to that, Omniglot only imposes marginal overheads compared to prior work that use memory isolation to deliver a weaker set of guarantees, often in the range from 0 to 3, 4, 5%. All right, so in summary, Omniglot enables safe interactions between Rust and foreign code by interposing on Rust's foreign function interface, integrating with memory isolation primitives, and then mediating all interactions with foreign code, maintaining memory safety, type safety efficiently. I would like to thank you for listening. I want to thank the reviewers, especially Shepard, Andrea Latuada, for their invaluable feedback, Zero Risk for providing evaluation hardware, and I'm happy to take any questions.